Okay, Sam, please tell us a bit about sequential drift analysis.
Yeah, okay, thank you, Aidan. So I'm gonna kind of uh, not go into a lot of details here on the individual algorithms, but I'll try to like summarize um, the general ideas and then just kind of mention a few things along the way. Um, okay, so far the drift um, the drift tests that I've been talking about have been on two, basically comparing like two data sets or two samples, and then trying to see is the second different from the first. And sequential is different because basically here, instead of just two comparison data sets or samples, we might have a series of data sets, again, or samples uh, that are ordered in time. And basically you want to detect, yeah, okay, you might have like some kind of initial data set D, and you observe these D1, etc. And you basically want to determine like kind of like at any time if the distribution of D is of the D's have changed. So just I guess in the easiest example, let's say that it's univariate and D, the initial D is like some kind of average value, and the other D's are single, again, numeric values. Basically, this could be like at any time if the average, maybe changes too much. So this is used a lot in like say assembly lines or kind of control of industrial processes. Um, okay, so again, we're at the sequence of values. Now, just on a high level approach, there's several approaches to these kind of detections, supervised or unsupervised, and usually hold on. Yeah, okay. So usually, again, there's supervised, semi-supervised, or unsupervised. In unsupervised kind of cases, it's either the thing that you're observing is, um, say, the classification prediction of a model, and unsupervised is kind of when xi or okay, so you use supervised basically when there's when for example there's some kind of ground truth to every data observations, and you want to kind of detect a change in say the ML model, um, and unsupervised algorithms, which is I think the more interesting and probably widespread, is basically again there's no kind of ground truth label. You're just trying to detect changes in kind of the distribution of what you're seeing. So again, it could be like the mean. Um, uh, the mean value is typically observe. You're trying to detect if that's changed or maybe the variance. Um, okay, that's again usually unsupervised detection. Um, okay, so um, okay, so I'm going to talk about unsupervised detection. There's if I've cited some works about like kind of a taxonomy of these various detections, but I'll just try to summarize the basic types, and most of the types are kind of they they differ on several one of several kind of axes or attributes. Um, so okay, usually what happens is that there's when you're observing something sequentially, there's two things that are being two quantities that are being compared. Um, uh, or it might be either two quantities or again a quantity as opposed to like a sample, for example, and then there's some kind of threshold to detect if the comparison is divergent enough, if there's change. So either again, this is usually the setup. There might be two samples that are being compared and continuously compared because the data is arriving sequentially, So maybe you have a sample that's like the more recent or the older data, and then there's the newer data, which is the second sample, things like that. And then again, you compare them and make some kind of decisions. So the main kind of aspects here are, again, there's parametric or non-parametric. Can you assume anything about the distribution? Most of the methods I've seen are kind of non-parametric because that's, again, more useful. The parametric approach will be like saying whether like maybe it's a Gaussian mean, and then maybe like the average value change from some pre-specified value to another value. Okay, a couple other aspects that are common are like the memory and the windowing of the algorithm. So like memory is kind of like how much of the past data does it remember when it's testing the newer data. So for example, it might keep some kind of summary statistics or transformations. And if it uses kind of like a moving window, there's the window size, which is the kind of if you know if the data is always the most if like xk to xt, t minus x minus k plus 1 is the window size. There might be like a fixed most recent window size. Again, some of these algorithms kind of have unlimited memory, so they always remember all the data, and then since the beginning of time, and then you again, and the memory can either be either the full samples or maybe the average of all the values in the past or something like that. So again, there's various iterations of these aspects. Anyway, and some of the methods are kind of like have two moving windows that maybe stay the same or possibly grow, but the windows are moving together over time. So that like the most recent data and then like the data before that, but not maybe the full history of the data. Okay, so again, there's different types. If there's a window size, maybe it's either fixed, like you have maybe two moving windows of size 20, and that 20 is fixed, or it might be adaptive, which means, for example, that if the data appears to be changing, it might want to like increase the window size to try to detect to get more kind of information about the change. And otherwise, if nothing seems to be happening, the window size might stay fixed. The other important thing here is there's online versus offline algorithms, and the basic idea is that the offline algorithm basically it receives a whole sequence and then of these data, and then tries to make the decision maybe like basically retrospectively. Tries to see at any point looking back, was there a change on the full data? And online algorithms usually kind of like they arrive in sequence, and the data continue to arrive, so there's no real end to the data. But an algorithm kind of has to decide by looking at the data in sequence and making a decision based on what it's seen in the past, but not the full data. So it can like make decisions over time. Given the data so far, has there appeared to be a change? But it may not reach, it might not end up seeing all the data that exists, or again, the data may not, if it's continuously arriving data, then the data may not even be there. So again, the consideration is often if it's something data cannot be stored, maybe you want to use an offline algorithm, or if it's data that's like just arriving over time, as opposed to a sequence that is fixed, then again maybe you want to use an offline algorithm. Also there's some algorithms detect multiple change points, other detect whether there was just one change point, and sometimes you have to say sometimes you want to specify, I think that there was one or more, you have to like say how many change points there were, and then it will try to find them. There might be some kind of optimization that occurs, like a penalty term that you have to specify that like for example, for a penalty for like overfitting or something like that. But ideally, you'd prefer an algorithm to work without having to accept a lot of user input. Okay, so that's the idea. Okay. Um, okay, so here's another thing. So sometimes the user needs to specify what the window size is, and this is kind of based on what the scale, or what I could call it, like a period of change of or that is expected to occur. And this is often not something you can know. So again, this is another thing that you might prefer that you don't is not required to provide. Okay, so I'll just mention kind of some algorithms. Um, uh, okay. Um, the adwin is a one of the particularly interesting or very popular method. I'll just say again, some of these methods operate only on binary values. Some are not. Some are continuous values. These ones are right now are only binary. Um, so for example, adwin is a method that you see the data has to be binary, and it's adaptive because it's adaptive. It's a window, but it's adaptive, meaning that the window kind of changes size. Again, in this case, you don't have to specify a window size. There's an initial window, and then kind of what happens is the you continue to like move the windows and then see if there's there appears to be kind of a change in the average values, because that's what you're detecting. If the average value of the binary values seems to be changing, um, if it, again it tries to change if there's no drift, it tries to it basically grows the window to see if it can collect more data. Um, maybe this means like the time scale for the drift has grown, and maybe there's no, you expected there to be change every 100 or something, and maybe you need to observe a window bigger to actually detect that there is a change. Because you want to capture a drift window has to capture kind of the change inside of it. Yeah, so again, this is an adaptive one, and it's again in many cases this is you don't have to specify the size of the window. Um, uh, okay, so just, um, and in continuous data, there's a few kind of moving window types like HDDM, which is a Hoefding. There's Hoefding bounds if you're familiar with a Hoefding drift detection method. It's not adaptive, but there's windows that move. Um, uh, there's a kind of like a before data and after data, and then it basically conducts it tries to test whether the before and after means change sufficiently, and then it uses Hoefding bounds, which kind of give a confidence. It's like a type of like false positive control on whether like any observed difference is significant enough if there wasn't drift. Yeah, it has a few different settings. KS-WIN is similar, except instead of the Hoefding test, it uses another test, Kolmogorov-Smirnov, to test if there was change. Actually, let me just go back to this one. This is one we used in a recent application, DDM drift detection method. It operates on the binary. This is the one we use for the ticket routing. It operates on the binary data, and the idea is it monitors changes in P, which is again the average value of the binary data, and then it raises an alert basically when the average seems to either seems to grow beyond some threshold that depends on kind of like the historical variability and average that has been seen for this sequence. It's kind of like a confidence interval. And we use this in a case where basically the threshold, the detection threshold is not fixed, but it depends on whether the data were very stable, or that's the standard deviation, or like what was the average value in the past. So if the data was very stable, meaning there were the standard deviations very small, the detection threshold is kind of very close to the current value. So only a small change would flag it. Whereas if it was more variable in the past, then the threshold would be, to be more conservative, would be farther away. So this is pretty simple and seemed to give actually pretty simple, pretty decent results. I tried a few of the other ones here, but they didn't seem as sensible. So yeah, sometimes simple is better. Okay, so I'll just mention there's two packages that implement a lot of these tests. I happen to use I used River. I couldn't get the scikit multiflow to work, but River implements like many of these tests. There's a few kind of other tests that are out there. Change Finder has a different flavor. Instead of kind of detecting like average value changes, it detects whether like the autoregressive, whether autoregressive means that you're doing a regression of a value on the previously observed values. So like like the current value might be, like, this is an autoregressive model. The current value might be negative 1.5 times the 1, 2 before plus 3.2 times the 1, 3 before, for example. Some kind of a regression model, basically a relationship that you believe is stable, where a value depends on the previous values. And this tries to detect if this fitted relationship changes. Again, it detects if there's a change in this kind of relationship, specified as autoregressive. So that's a different kind of flavor. That's not simply about whether the average value or something like that changes. I haven't tried this myself, but it seems to be popular in like kind of time series data. There's a few. Okay, now I'll just mention a few things in the multivariate case. So a lot of the so far the multivariate ones that I saw are offline, meaning that they're retrospective and kind of they're given the data. They try to partition the data, a sequence of data retrospectively, and kind of detect a change point. Basically, see if there's if there are points where, if I look before and after this change point, there seems to be a change. And if there's no change point, then basically you can represent the entire sequence as one segment. Otherwise, you can partition it into several segments where there's a change point between each separating each segment, and then basically within each segment, there's a single stable distribution. So one of these algorithms is called the energy change point. I haven't used this personally, but it seems to be successful, and also it's univariate. Also it works on sorry, it's multivariate, but it also could work on univariate. You don't have to specify kind of any prior distributions or anything like that. And a lot of these algorithms kind of work by kind of like a divisive approach. where you have the data, kind of like think of like a decision tree. You have all the data. You can see if I can find like one spot that seems to maximize the difference, and if like the difference after separating it is significant enough, then I make the cut, and then I continue splitting if I can. So that's kind of like a common approach for these methods. Um, uh, and okay. There's also another library that I was reading about called Ruptures, where it's univariate or multivariate data, and uh, this has a lot of capability, where so it's an entire suite. Basically, you can simulate data with different kind of properties, and and um, and then try to detect them with different drift detectors, and the drift detectors basically have different cost or kernel functions that determine kind of where they optimize, where they try to split to maximize some kind of a target. You can also create like some custom cost functions. You know, I'll give like one example. Uh, you know, there's the squared loss, which is the simplest one. Basically, it tries to segment on the assumption that basically that if the mean value in the segment is significantly different enough, and then the cost basically is this you apply the kind of the costs on each segment and see if if those are too high. And there's other kind of other kind of costs cost functions here. Okay, so the last thing I'll mention is statistical control when doing things in a sequence. So if you remember from the hypothesis tests, this is something very important. A p-value guarantee is only valid basically when performed once. So for example, so what does it mean that you have okay, so say that you have you're performing some kind of test, and you have alpha is 0.05. Okay, that means that that means that if the two distributions p and p prime that the two samples came from, say for example like a t-test, this means that if the two samples are actually have the same like underlying mean, then the probability that you'll get two samples that seem to actually have a significantly different mean is only 5% of the time. And that's how you make the guarantee. That's how the guarantee is that when you detect something that it should be significant, because the probability of it happening by randomness is very low. But the problem is that this only valid because you did the test once, you got a result, and the probability of it happening, I think I mentioned this before. Probability of it exceeding becoming a false positive only happens in 5% of the random samples. But if you do this more than once, and you say like if you say like I'll detect if at least one of the p-values is less than the threshold, then the guarantee no longer holds, because the probability of at least one happening by random chance is actually ends up being much higher than the p-value. So basically the thing is that I'm trying to say is that when you do a sequential test, you end up kind of doing a test multiple times, maybe when comparing two windows, and if the detection threshold is based on like a typical p-value, if you're doing something repeatedly, it may not the the actual like guarantee may not hold anymore. And it seems to me that Eitan, do I have like 5 more minutes?
Sure, go ahead.
So it seems to me that like most of the algorithms don't seem to really take this into account. Like again, they just use the one-time thresholds simply. And one of the okay, so for example, the add when criterion, it does this there's a false positive control, but it may be that that if you're trying to like make a detection only once and and have that be really a false positive guarantee, then it may not hold, although experimentally seems to be okay. So there's one algorithm that I'm aware of that actually does this, and we've used it in a few applications. It's called CPM. It's so far as I can see, it's only available in R, but you can connect to it through Python. And this has a true false positive guarantee in that basically when it makes the detection, the probability of okay, so say for example you're trying to detect whether the average value changed, okay, and that would be drift. The probability if it detects a false positive means that the drift has not happened yet. A true positive means the drift happened at some time in the past, and obviously you want to detect as quickly as possible after that happened. Because it's easy to just wait forever and then just say something happened in the past, and the likelihood of being right is correct. It's difficult to detect it quickly. So how this algorithm works, it works kind of like how you think it would work. It takes at every time point, it looks at the past values, and then it tries to split it at any time point into before and after windows. So W0 and W1, okay? And then it sees if any of the before and after pairs, it measures the divergence on every pair, and then if any of them seem significant enough, then it detects drift, and then the change point, the predicted change point is the point that separated those before and after. So you predict when it happened, and also you predict that it happened, and also when the change point occurred. And the important part here is that there's false positive control because over time, basically as you're performing more tests, the threshold of making a decision actually rises. So if the longer you have to wait for drift to arrive, it's basically kind of more conservative in a way, and that the drift has to be more significant to be detected. And so basically this has a real guarantee that at every time point, if you make a detection, or the probability of making a detection when drift has not occurred yet is the alpha that so it actually has the right false positive, and the probability yeah, right. Yeah, the probability of not making a detection is sorry, yeah, whenever drift is detected, the probability it's a false positive is always the same alpha. So again, because it has to look at the full data, it may get a little expensive, but I've tried this on like 10,000 data draws, and it works. It takes a few seconds. So if you have like really long data, maybe not a good idea, but for like decent amounts, it works well. It's easy to use, and also there's several different tests. You can not only detect for a change in mean, you can detect for there's Kramer von Mises, which detects arbitrary distribution changes, and we use this in one of our papers to just detect if there is like an arbitrary distribution change. So it's flexible and it works well. And if you're interested, I cited one of our papers here. Yeah, so that's basically what I wanted to talk about. Um, any questions?
But one quick question: if why do we need the sequential? I mean, I could repeatedly use the pair test that you were talking about before. Can you clarify that point?
Well, in general, you want to use it. It might be appropriate. Wait, sorry. When you mean sequential, you mean the CPM, or you mean like
In
sequential detection?
general,
Well,
yes.
it depends on your data, because if sequential data has a sequence, it arrives in time. So here, so I'll give you an example. Say that you have 100 observations, and 50 of them have average 0, and 50 of them have average 2. Okay, drift would be like the first 50 observations and then the second 50 observations. If you mix them up randomly, the average doesn't change, so that wouldn't be drift. The drift happens specifically because there's a before and an after.
Mm, mm, I
So
see.
you really have to take in the fact that things are happening, like there's a change point and it affects things after it.
Mm,
So it's not. I mean, they're random samples, but you might assume that they're random samples, but the point is that the sampling, the distribution changes at some point.
I see. I see. Okay. Any other
This
questions?
seems very important, because my guess is that a lot of the data we do get does change over time, right? So, like, for example, if you're monitoring a test and you are looking at certain variables in the test, and then next year you do another test, right, of the say a power server, you may find that things have changed, right? And if you trained based on the older data, it's not going to be valid for what you're doing now, right? And I'm just guessing that a lot of what we do has that deficiency in it, right?
Yeah, I agree.
Yeah,
This,
right.
this is
I
very
get the other aspect is that it's not necessarily just that you're looking at each data in sequence, and then testing that to like the baseline. You might be testing, so it's not just a sequence of like single tests, it's also can be that the data accumulates over time.
Mm.
Like for example, the moving windows, for example. Like the baseline, if you have a moving window, the baseline is also the baseline, which is like the previous data, also changes over time.
Yeah, you have factors that will be changing things repeatedly, not only once.
Right.
Okay. Um, any other comments, thoughts, questions? Okay, Sam, so thank you very much for this overview on the drift detection chapter.
Yeah, thank you. Yeah, please let me know if you have any questions about it.
Okay, great. Right, so next meeting will continue with a different chapter. I'll start talking. It's going to be about best practices and pitfalls. Okay, thank you very much for joining today. We'll continue next time.